talk of this session is going to be given by Quentin Ducasse, and this is going to be about how to test new hardware extensions, new hardware features when you're developing JITs. I hope.
Yeah, thank you for the introduction. So, my name is Quentin Ducasse. I'm from the ENSTA Bretagne in France. So this is joint work with my PhD advisors, so Pascal, Cotret and Loïc Lagadec. And I'll present to you Gigue, which is a JIT code binary generator for hardware testing. So what does it mean? I'll first go into some context and background. So I'm sure most of you are familiar with VMs, so I won't dive in this figure that I believe is maybe incomplete. But one thing that I would like to highlight is that the JIT code region is a key component because it is both performance critical in the sense that it has optimized machine code, and it's also security critical because it's usually a part of memory that has to handle both writable and executable memory. And as you might know, this is usually a bad sign of vulnerability, that you can be vulnerable to code injection attacks, code reuse attacks, and so on and so forth. So there is a history of attacks. So I mentioned code injection, there's also code reuse. We can also attack some of the VM internals. For example, even if you have secured your JIT code region, you might just give it as input malicious bytecode that will just generate malicious machine code in VM. So I would just like to highlight 3 state-of-the-art defenses that I think are very interesting. So first one is called JIT Guard, which uses Intel's GX, which is now deprecated, but which is a secure enclave that has encrypted content that is decrypted on the fly. So this is to accelerate and protect the JIT compiler. Then we have Nujitsu, which uses intra-process isolation with memory protection keys. So they manage to handle some of the permission checks in the user space and accelerate while keeping security guarantees. And the last one, which dates from last year, which is called CITIS, uses Intel CET, which is a control flow enforcement technique that stores a shadow stack somewhere in memory, and that also performs indirect branch tracking. So what I want to highlight with these 3 papers, which I believe are very good reads, is that there is a definite need for hardware-enforced security due to the performance it manages to squeeze out for performance-critical components. So now that this is the context of why we might need some hardware features, I'd like to give some background on the Pharo VM, which is our mental model for the design of Gigue. So Pharo VM uses an indirect thread interpreter, a linear non-optimizing method-based JIT compiler that we recently ported to RISC-V. And usually what we have is the VM source code that's written in restricted Smalltalk that we had a talk earlier on. So that's called slang. That we then transpile to C, and we generate the executable on which we can execute the application. We also have a test framework in which we manage to do black box testing of the JIT compile code using a CPU emulator, which is named Unicorn, and I will go back on this more later on. And so I tried to motivate why we would need hardware security features, and now I'd like to motivate why the RISC-V ISA might be a good candidate for that. So if you haven't heard about it, it revolves on 3 main objectives. First one being open source, in the sense that the standards that are open for everyone. You can still modify and do a proposal for instruction groups that are still being drafted. It's also modular, so you have instruction groups that are separated to support a wide range of applications. So as an example, we have the base one, which is I for integers. We have multiplication, and so on and so forth. And if you manage to design a core that supports the RV64, INA, FDC extensions, this means that you're ready to support the fully featured OS such as Linux. We also have several standard allocated spaces for extensions. What does that mean is that there are dedicated opcodes, so that are named custom 0 to 3, that are fixed in the standards and that won't be used by future extensions. So this means that any change that you might want to make now will be available in the future and will not overlap with another instruction group. We also have some hints, which are instructions with specific arguments that fall back to being an op if they are not implemented. So for example, here the LUI x0 and value is usually the load upper immediate, so you would take the 20 upper bits of the value and load it in the register. If you pass it the register x0, which is the hardwired 0, this will do nothing, but you can implement some logic in your processor to actually do something. So I talked about why we might need custom instruction, but which custom instruction I'll be talking about. So the first example, which I'll call E1, are simple rotation instructions that are not actually fixed in the RISC-V standards. So they are very basic rotation instructions that you might expect. The second one is the use of a shadow stack. So you can just put two new instructions, CFI call, that you would put right before a call to store the return address in some part of your shadow stack, and CFI return, where you'd have to pop the return address and compare it to your actual return address to see if the control flow has been disrupted or not. And the third one is duplicates all memory accesses and tags them with a domain. So this means that, for example, we can use it to put in the JIT method, the JIT code region could only use duplicated memory accesses that are tied to a domain and that can only access the data in the JIT region. We also put some specific change domain and rated domain instruction that allow the switching of this actual domain to be performed. So, some motivation design of Gigue. So, in the team, we are mostly hardware developers, and when we would like to make JIT-specific extension, JIT-specific custom instruction, this means that we have to support the whole software stack. And as RISC-V is still unstable, we'd like to get something way more simple and flatten the stack to get a meaningful representation of what might be the JIT code region. So we do some assumptions. First, that the JIT and ahead-of-time compilers are the only components that are modifying machine code, and then that a snapshot of the JIT code region is representative of the changes that are made by those components. So this means that if we manage to get the JIT code region after a certain amount of time, we might say that if we get this one, it's representative of the application that's running. So our motivation is to flatten the software stack significantly so we can speed up hardware development and support VM-specific custom instructions. So, Gigue, which is the French for jitter in signal processing. So it's a workload generator. It's a random workload generator that will produce an executable file modeled after the JIT code region and support custom instructions ready to execute on extended cores. So we designed it around three main ideas: parameterization, so it takes in-input qualification parameters to qualify diverse application and VMs. It's modular in the sense that we'd like to extend it with custom instruction, we'd like to extend it with custom JIT code region constructs, and it does heavy use of testing, so we have lots of sanity checks, and we have a custom execution model to validate the binary we generate before running it on the real or simulated hardware design. So the three main components are very simple. There are methods that are filled with random instructions and calls. We have a model for polymorphic inline caches, which is basically a number of caches and then our methods. And we have some trampolines to manage the call to and for the interpretation loop. So our binary structure, which is self-contained, is we have an interpretation loop, that calls all JIT elements in a random order. Then we have each JIT element that will call a number of other elements, and both have access to the different trampolines for routines. The resulting binary is compiled using the binary framework provided by the RISC-V assembly test. So this means that it will automatically be supported by the different RISC-V core that support this assembly test suite. So for parameters, I will go quickly over them. Basically, they are split into what qualifies your VM, what qualifies your application. And we would say that for a VM, we have a JIT code region size that we fix, the frequency of the different JIT elements, so methods and inline caches, the different usable registers that we might need, so we control the environment of our generated binary. And then for the application, have number of methods, the difference we might want to inject in the method size variation, the call occupation, and we can also, and the one I think is interesting, is the frequency of instructions. So if we want to have, a binary that's very memory intensive, we can change that. And also we can specify the shape and size of the data. So the binary generation works using two components. One is a generator, which is responsible for the higher level structure handling, and a builder, which is just responsible for instruction emission. So it goes as follows. First, we'll instantiate the trampolines. Then we determine the method base size using the fixed JIT size and the number of methods. And then we'll instantiate the different elements that all insert the same API. So we just go through the different weights that we provided for them and instantiate them. Then we'll fill them with a random instruction following the distribution that we chose. We'll patch calls, so the call graph is fixed at binary generation. Then we'll generate data and link it in a self-contained binary. So as the generated binaries contains random instruction, we have to perform some kind of sanity checks. So the registers that are used are fixed at generation. We sanitize jumps and branches so that they don't break the call graph. Data accesses are indirect through dedicated base registers, and we perform the call patching when the whole call graph has been fixed. And one thing that we wanted to enforce is that the binary execution is correct. So we extended it with testing, which I will just come to. So modularity and the test framework. So if I come back to the three examples that I presented earlier, so to include the different instructions in the Gigue framework, so for the first one, we've added the instructions in the random generation of immediate instructions and register instructions. And I would argue that this adds, 100 lines of code. Most of them are boilerplate code, and that's why I just written on the side 12 lines of code. So this means adding them to the random generation and simply in the correct place in the code. So this means overloading the builder, random I and random R generation. For CFI call and CFI reads, so the shadow stack custom instructions, they are added to the method call epilogues, so right after the return, and they are added at call generation. And same thing, it adds two instructions, and I'd argue that this adds 12 efficient line of code. For the last one, so we added 15 instructions, and we completely replaced the random generation of stores and loads. When we also changed the method epilogues and code generation so that we check and sanitize the domain that we're jumping to. So for this one, we add a bunch more lines of code, but once again, I would argue that this is basically 54 lines of code. So the test framework we define is based on Unicorn, which is a lightweight wrapper on top of QEMU. It defines flexible wrappers that are triggered in events such as exceptions, memory accesses, or register values that are being reached. We extend them to catch custom instructions as defined in the standard. So this provides an easy API for the user to add a custom instruction that will have an effect in the software test. So for the rotation, what we do is when we catch the rotation, we'll simply perform the rotation on the result of the two registers, push it back in the unicorn state, and resume the execution. For the example 2, we'd store a list with the return address on the software side, and just push and pop to and from it. And for the third one, we add a tag of domains to duplicate instructions, and we ensure that we're in the correct domain when we're executing, and fall back to the traditional load and store. So I will just show you a certain use case that we've used Gigue for. So the hardware development stack that we have to go through to extend our core with custom instruction looks like this. So this is without having to put a VM on top. So first we have our core definition, so our processor implementation that's written in a high-level hardware description language, which is called Chisel, which is an extension of Scala. Then we compile this Chisel language description of the core down to Verilog code, system Verilog code, sorry, which is another hardware description language that we have to use. And then once we have this, we have the choice to either go through the synthesis tool to get down to the bitstream and put it on an FPGA, or go through a simulator, a cycle-accurate simulator, which is what we do. So we can execute the Gigue binary on this very little simulator. So it is able to run a fully featured OS, but it's extremely, extremely slow, and we cannot go through it to validate that. So that's why we'd like to have a binary that models this JIT code interaction and give us some insights on whether our custom instruction is suitable for a JIT compiler or not at all. So as an example, we took some values from the Faro VM dumps and artificially extended them to generate different application classes. So, can you see my mouse? Yeah. So on the left, we made a varying call occupation. So what that means is if a method in the JIT code contains loads of calls or not. And on the right, we use varying memory accesses. So this is on the core that simply implements the E1, so the rotations. And we wanted to see if we can artificially inflate the number of application classes that we have, so we can have a meaningful workload to work on. So, as a conclusion, I presented Gigue, which is a workload generator for hardware testing. I believe that it's parameterizable to qualify VMs and applications. It's modular, so we simplified the addition of elements and instructions and provided a way to test your custom instruction before adding them in the actual hardware. We are implementing variants of E2, so the shadow stack, and E3 in an actual core. And we'd like to compare them because usually when we have a paper presenting a shadow stack, they will compare to the software version, and usually they're faster. And same thing for the example number 3. We like to have a common ground to compare different solutions and to provide insight on what would be an interesting fit for a JIT compiler. And yeah, and the Faro VM already supports the E1, so which is just a rotation, but it supports it in its custom testing environment. And the final step that we would like to reach is to have a complete stack running, which means the core implementing custom instructions that might be interesting and that we can propagate through the VM and running on top of an OS. But we're still far from there, and this is just a way to flatten the stack and try to have some preliminary results. So thank you for listening to me. The code is available open source on GitHub, and I actually have some questions to you. So, which custom instruction would you integrate in your VM JIT code? What does it mean for you to integrate custom instructions? And also, which parameters would you qualify the JIT code for your VM? So I have much more details in the paper on how we use the parameters to generate binary, to have a representation of this piece of memory. But I'd be happy to hear your thoughts. Thank you.
So this is going to be probably the first talk when, if you come to the mic, you can either ask a question or provide a response. So please go ahead.
So you were mentioning 3 different extensions or sets of instructions that you were adding, and you were saying they were based around security, and the second and third, I definitely see that, but how is a rotation a security primitive? I didn't quite get that.
Oh, no. The first one is just an example of a very simple one that we can extend. It's definitely not a security one, sorry. Yeah, maybe.
Okay, so everything made sense for me with the one exception, which is I didn't understand the random generation thing. Because if you have a JIT and like you just want to extract an executable subset of that, why don't you just grab like lots of them from a real JIT workload and take those and then feed them into your core? Like I didn't quite understand the random part.
Yeah.
Do you like explain that again?
Yeah, of course. So we made that choice because actually it was easier to control the environment on this subset of, how to say, we would just qualify the dump of a Faro VM, so after running some kind of application, and then we can get some metrics on the used instructions, on the number of polymorphic inline caches in comparison to the methods, and then we try to artificially expand that on something that we can control a bit better. So which is, we control the registers a bit better on the
So it's almost like a fuzzing like approach, except you're trying to mimic you're trying to match statistically the like number of load, store, compare.
Exactly.
Things. Okay.
It was a bit, how would I say, faster for us to do this way, and it by no means replaced the actual JIT compilation.
Okay, that makes more sense.
Yeah, thank you.
Any more questions? If not, let us thank Quentin one more time.